Hey guys, we're almost done with solutions. We want to talk today about colligative properties. Warning, you put that thing into Microsoft Word and it doesn't even know what that is. So we're going to talk about colligative properties, or something that's very important to you personally in how you live your life and some of the things water does for you. So colligative properties are the properties of a solution that depend only on the number of solute particles and not upon their identities. So for example, how much salt or how much something did you dissolve in water, and that's what's going to impact the water itself, okay, not what it is. There are 4 colligative properties you need to be aware of. You should write them down, right? And we're going to talk about each one individually. Right. It's important to realize, to think about what water is. Remember, water is polar. So when we have this molecule of water, we have a negative end up here by the oxygen, and we have positive ends down here by the hydrogen, which means they attract each other. So if, again, I think about water, I have molecules of water, and they attract each other. The positive end of the hydrogen over here attracts the negative end of the oxygen, and they form these things called hydrogen bonds. And again, these are attractive forces. They are not bonds. The covalent bonds that you see are within the molecule itself. I realize we probably said that about 10 times in the past few podcasts, but that's important to understand, that these are simply attractive forces. Now, they are very strong attractive forces that hold the water together. Now, as water moves, as it's a liquid, then these molecules will go and hold on to other molecules. So the molecules are constantly moving, so they don't stay in that position in a static form like they would in ice. So when you get water freezing, the water actually lines up so that you get, for example, here is a molecule, all right, and it gets attracted to other molecules, and they line up so that the positive is next to the negative, right? And these blue things, the things that they refer to as the hydrogen bonds. Now, it looks a little strange because you don't see a bunch of these molecules. You see one here, all right, but then, and you see one here, right? But then all of a sudden you look here and there's not a complete molecule. Well, that's because it's in 3 dimensions and the hydrogen's going back into the board, if you will, and you can't see it, okay? But so you have to think in 3 dimensions, so it creates this 3-dimensional crystal that we call water. But most importantly, what you'll notice is they're holes, right? There's this big hole right here in the water. What is that? There are holes over here. So what's in there? Well, frankly, the answer is there's nothing in there. And that's why when water freezes, it gets bigger, right? Because these molecules all line up exactly right, and they push the other molecules away. And unless you're sitting right at the surface where you can add in some oxygen, right? When you're down here, you can't add in oxygen underwater. It's not already there. So as a result, it just gets bigger. Well, when water's trying to freeze, all of these things have to line up just like this. What happens if you throw some salt in amongst the water freezing? Well, if you remember, the salt will say, well, here, over here is chlorine, and I'm going to line up all of these water molecules around chlorine, right? Because chlorine is very negative. It's more negative than the oxygen is. So they get very attracted to the chlorine. So what does that mean? Well, that means it can't freeze. Well, that means the water molecules, which normally would line up this way, can't line up that way because there's salt in the way, because they're more attracted to the salt than they are to each other. So as a result, this stops the water from freezing. So it means the water has to be colder to actually freeze, or it stays a liquid longer as you cool it down. Take your pick either way, right? So when we add a thing of sodium, let's say, of sodium, Na, and it's positive, right? Well, this molecule here is going to turn around so that this oxygen is attracted to the salt, and this oxygen is going to turn completely around, so it's attracted to the salt, as is this one, and this one, and this one. So as a result, they can't form this nice crystal lattice work over here, so they remain liquid. Okay, that's what's going on, kind of in simplistic terms, when you add salt to water. So when we add ice cream salt and you're trying to make ice cream, and you add it to the ice that's here, this ice, instead of being at 0 degrees Celsius, will get colder, and it will melt, freeze, whatever, at about 10 degrees, 15 degrees below 0 Celsius. When we take ice melt and throw it on the road, even though it's cold, even though it's below 32 degrees Fahrenheit, the road becomes a liquid. Right? And the reason for that is we have added salt to the road, and it's preventing the ice from freezing. We do that with antifreeze in your car. So back behind the grill of this truck, there's a radiator right here. You should be able to see it. And you put antifreeze into your water to prevent it from freezing so that you can still drive your car when it's cold outside. And in fact, if you go and you put in a 66% mixture of water and antifreeze, that will hold your car down to negative 90 degrees Fahrenheit. So the water will not freeze for a really, really long time. Normally it freezes at 32 degrees. Right? But the more antifreeze you add, the colder it gets before the water will freeze. Now, it is interesting that antifreeze itself will freeze at about 10 degrees below 0 Fahrenheit. So it's the fact that this is a mixture of the two that makes the difference and makes these colligative properties happen. So the second colligative property is boiling point elevation. So when you boil water at, let's say, 100 degrees Celsius, right, it boils and that's fine. But if you put salt in that water, or you put antifreeze in that water, these molecules over here, these ions, are all attracting the water molecules back to them, right? So as a result, the water does not boil as easily. So it might be 110 or 120 degrees Celsius when the water actually boils. So it prevents things like your car overheating. That's what you want to avoid. So what's happening here, let's look at it a different way. If your range of liquid water is from 0 degrees Celsius to 100 degrees Celsius, well, what we're doing by adding antifreeze or adding salt is we're making that range be higher. Now, depending upon how much salt or how much antifreeze we add, we could be at negative 20, negative 30, negative 40 degrees Celsius. And we could be at 110, 120 degrees Celsius. So we have made water remain a liquid for a longer time. So we have lowered the freezing point and we have raised the boiling point. Now, something else that we've done is we've reduced the vapor pressure. Water tends to evaporate. Remember that we had a chart that told you how much water pressure, vapor pressure there was at a certain temperature. Water tends to evaporate all the time, right? No matter what its temperature, water's evaporating. But if I throw salt in there, then the water, again, the water molecules are attracted to the sodium, they're attracted to the chlorine, and as a result, the water molecules don't tend to leave as easily. So salt water does not evaporate as quickly as lake water or river water, for example. Alright, and the final thing is osmotic pressure. Now this really is a biological concept, but we might as well mention it since it is one of the 4 colligative properties. If you have a solution that, let's say, is 0.1 molar, again, let's say salt, and we have one that's 1 molar, what's going to happen is the water that's over here on this side is going to actually transfer over to the right. And it's going to do that because it wants to keep these two numbers the same. So we end up with something over here where the molarity of the two waters, the concentration of the salt, is about the same. So we have created, obviously, more pressure over here by the water coming over. Right? Think of it as you go out and you eat something that is very, very salty. The water gets, the salt gets into your bloodstream and goes to your cells. Your cells will go and absorb the water. Will absorb the salt. So if you have a cell and it has a bunch of salt in it, well, the concentration of salt is higher, like this. So the water will start to enter your cell to compensate for the extra salt. Well, all of a sudden that means you're retaining water. You retain water weight and or you get bloated. You feel that heavy feeling. Okay? So That's the concept of osmotic pressure as well. So those are your 4 colligative properties: the freezing point depression, boiling point elevation, vapor pressure lowering, osmotic pressure. You need to know what they are, and you need to focus on the first 3, because the first 3 are what we focus on in chemistry. Alright, that's it. End of this video. Only one more to go. Have a great